So this is a continuation of part A that we just did in the previous video. Now determine the weight of an object that would cause an extension of 0.86 centimeters on the same spring. So in this case we are given the extension caused by the weight that we are yet to calculate. But bearing in mind that we're talking about the same spring, therefore we are still talking about this spring constant. So we're already having our spring constant K to be equal to 4,000 Newton per meter, while we are having the force or the weight that we are supposed to look for, which will be equal to the force, and that is what we want, but we are having the extension to be 0.86 centimeters. But this extension, we are supposed to use it in the SI unit, and therefore we convert this into meters, which therefore becomes 0.0086. We divide it by 100, since 100 centimeters make 1 meter. From here now we say, from the Hooke's law, force is equal to spring constant times the extension, and therefore we are talking about the weight, which is the force which we are looking for, should be equal to our spring constant, that is 4,000 Newton per meter. We multiply by the extension, which is 0.0086 meters. Now the meter will cancel with the meter. Then we have 4,000 newtons times 0.0086, which now gives us a force of 34.4 newtons. We can then proceed to number 2. The identical springs of spring constant 3 Newton per centimeter are used to support a load of 30 newtons as shown. Determine the extension on each spring. Now in this case, we need first to get the spring constant in the SI unit, which is Newton per meter. And therefore in this case, we are simply converting this 3 Newton per meter to be, maybe we're talking about the spring constant as 3 newtons per meter, per centimeter. That means you're talking about 1 centimeter. So it is this 1 centimeter that we convert into meters. So we'll have 3 newtons over 0.01 meters. So this gives us 300 Newton per meter as our spring constant. We then now say, since these are two springs, maybe we can talk about spring A and spring B. So since they are connected in parallel, then it means that they are sharing this weight, the 30 newtons. So it means spring A is going to experience a half of this weight, and spring B is also going to experience a half of that weight, and therefore the extension in one of the springs will just be equal to the extension in the other. So extension in A, we can say extension in A is equal to extension in B, and weight or force in A is equal to force in B, and that force in A or B is equal to 30 newtons divided by 2, since we have said they share the weight, and therefore that is equal to 15 newtons. So if you want to get the extension in A, we simply say it is force in A all over the spring constant K. Remember, the spring constant is common for the two of them, so we are using 300 newtons. So that one was first approach. The second approach, we can say alternatively, we are talking about two springs. So when we add the two extensions, they should give us the full extension for that system or that arrangement, and therefore we can say that the force that is experienced by the two springs together can be equal to the spring constant times twice the extensions, because we're talking about extension of the first spring A plus extension of the second spring B, and therefore we'll be talking about 30 newtons being equal to the spring constant 300 Newton per meter times 2 of the extensions. So we'll be talking about 300, or rather 30 newtons divided by 300 Newton per meter to be equal to 2 of the extensions, or twice the extension in one spring, because the extensions are equal. So we'll be talking about 0.1 meters to be equal to 2e, and therefore extension is equal to 0.1 divided by 2, and this gives us 0.05 meters as the extension in either A or B.